Okay, so we now had Thomson's plum pudding model of the atom, right? Where you had small negative electrons embedded in a positive sphere of charge, the plum pudding model, electron plums and some positive pudding. So this was pretty cool, right? This was exciting. Atoms had been indivisible up to this point, but now with this new thing that Thomson had shown, that there were these little negative charges, these electrons inside atoms, well, atoms are divisible. They are made up of something. They're not the smallest unit of matter, right? So a lot of scientists were really interested in saying, well, let's look at this atom then. Let's look at it closer. What's in there? What are the parts of it? What else is going on, right? One of these scientists was a guy named Ernest Rutherford. He was from New Zealand. And so one way to study what's in an atom is shoot stuff at atoms and see how the stuff you shoot at it behaves, right? So he shot alpha particles, which are pretty tiny, at gold foil. Now, gold is number 79 on the periodic table, which even then they knew meant it was a pretty big atom. Now we have a better understanding of why that is, right? So taking these tiny alpha particles, shooting them at this big gold foil, and just seeing what they do. Now, in Rutherford's time, they didn't exactly know what alpha particles were. They knew they were given off by radioactive decay, which is for a topic for chapter 16 next week. Okay, but we did know that they were positively charged and much smaller than a gold atom. Now, just for some added context, you know what an alpha particle is, or at least you should, okay? It's just a helium nucleus. It's 2 protons and 2 neutrons. But all you really need to know to understand Rutherford's results is that they were positively charged and very small compared to a gold atom. So what do we expect? Well, Thomson's model was the widely accepted model at the time, right? It was the newest thing. It was the best picture we had of the atom. And so remember, in Thomson's model, right, yes, there's a positive charge there that's canceling out with the negatives that we now know exist, but it's fairly evenly distributed, right? It's a nice, even positive charge. No one place is very positive. The positive charge is not dense. The charge distribution is of a very low density. No one point on there is very positive. It's just that the whole thing is positive, so it adds up to cancel out with those negatives. So we would actually expect that when we send these positive charges through, since it's not very positive anywhere, it should just kind of go straight through. That is not what happened, okay? When Rutherford actually did the experiment, he noticed that most of them passed straight through, but about 1 in 8,000 deflected pretty strongly, and some even bounced straight back. I'm just going to show you a video so you can visualize the experiment here, and then we'll come back and talk about it.
The nucleus of an atom was first discovered when a beam of positively charged particles emitted from a radioactive source was aimed at a fluorescent screen. The particles caused the fluorescent screen to glow. When a very thin sheet of gold foil was placed in the pathway of the particle beam, a few particles were deflected to the side. Occasionally, particles were deflected straight back. But nearly all particles passed right through the gold foil, as if it were not there. The scientists concluded that atoms must be mostly empty space, and that because some particles are deflected, there must be a small positively charged central mass, which they called the nucleus.
So when Rutherford saw this, he actually said it was one of the most surprising things he'd ever seen in his life. It was a shocking result, right? These alpha particles being deflected or being even rebounded. He compared it to, it was as if he had shot a cannonball at a piece of tissue paper and the cannonball bounced back and hit you. So the cannonball being the alpha particle and the tissue paper being the positive sphere that's part of the atom, right? So why was this positive sphere supposed to be like a piece of tissue paper? Well, again, if it were evenly spread out, as it is in the Thomson model, then no place in the atom would have a strong enough charge to impact the trajectory of the alpha particles, right? Yes, there's an overall enough positive charge to cancel with the negatives, but it's spread out. It's not that positive in any one place. And so since some were being deflected significantly and even rebounding, this spread out positive charge can't be what's really happening. Most of them are going through, but some are encountering something that's positive enough to actually deflect or rebound. Then this positive charge must not be spread out so that it's kind of weak everywhere, but it instead concentrated in a small space where, yes, overall, the positive component of the atom's charge is the same. It's just enough to cancel out the negative, but it's not spread out thinly. It's actually very concentrated in one spot. So this relatively small concentration of positive charge is what we would go on to call the nucleus. Okay, let's just kind of look now at the many conclusions about the atom that were drawn from this and see if we can kind of justify the thinking the same way Rutherford would have had to. So one conclusion that was made was that the nucleus is positive. How do these observations support that? Think about that, answer that in your head. Okay, well, what did it do? It deflected or even rebounded alpha particles, which are positive. So by the law of charges, if they're repelling positives, it must be positive. The nucleus had most of the mass. Why? Well, remember, we knew the charge to mass ratio of the electron from Thomson. We even kind of now had a charge of the electron from Millikan, and we knew the mass of a gold atom. The electrons did not account for enough of the mass, right? So we did already kind of know that the positive charge was going to make up most of the mass, right? We knew the mass of the electrons was tiny. This is actually technically nothing new from Thomson's. It's just that this mass was not as spread out as we thought, right? It was much denser, very concentrated in this nucleus, as we started to call it. The electrons have little mass. Why? Well, again, from Thomson and from Millikan, we kind of already knew that. But once we factor in the mass of the neutron, we find that there's almost no mass left to be attributed to the electrons. It's all used up pretty much just by explaining the nucleus. It's like a rounding error that could belong to the electron. Okay, so most of the atom is empty space. Why? Well, we now know that the nucleus is tiny, very concentrated, right? And yet there's enough room for all of these alpha particles to go by. So these nuclei can't be packed in right next to each other, or how does the alpha particle get by, right? So if it looks like this, so if the gold foil looks like this, if these are all nuclei, how is an alpha particle supposed to get through? Unless the very concentrated amount of charge as the atoms are packed together is at the center, and so most of the atom ends up being empty space. We'll actually also look at how Rutherford quantitatively calculated the size of the nucleus, but this is just kind of looking qualitatively at how we can start to get there even just by thinking about it. Now, he also reasoned that the electrons would orbit the nucleus like a planet orbits a star, right? There you go. That's where you get the name the planetary model from. Why? Well, if it wasn't moving around the nucleus, electrons are negative, nuclei must be positive, so they would be attracted together and all matter would kind of just collapse into itself, right? So they avoid this. So they avoid this the same way the moon avoids crashing into the earth, right? By having some tangential velocity and being in centripetal motion. So, but instead of gravity being the centripetal force here, it would be the electric force, right? And you can see there, if it ever stops with that tangential velocity, it will collapse into the nucleus, just like the moon would collapse into the earth if it was not for its tangential velocity. Okay, so this model is one of a few planetary models, actually, but you technically already know enough about physics to understand that there is something fundamentally wrong with this. It cannot be right. Pause the video, try on your own, think about this. I want you to think about Maxwell, think about Unit 3 in general, think about what Planck told us, and see if you can come up with why, right from the get-go, there was a problem with this. In fact, even Rutherford kind of knew this doesn't work. Remember, these are models of the atom, right? Models are a tool we use in science to try and better our understanding. They're not necessarily meant to be the truth, okay? So Rutherford said this model can explain some stuff, but even he knew there was a big issue here. What was it? Well, as you know from Physics 20, if something is undergoing circular motion, right, it is accelerating. It's accelerating centripetally. Even if its speed is constant, its velocity is not because the direction's constantly changing, right? So it is accelerating. Okay, if you didn't pause before, definitely try pausing now and now see if you can figure out what might be wrong with this. But what did we learn in Unit 3? An electron is a charge. It's accelerating. What's it going to do? It's going to emit EMR, electromagnetic radiation. And then what do we know that electromagnetic radiation carries, or is, I guess you could say? It's energy. So if this electron is emitting EMR, and EMR is energy, then the electron is losing energy. Now, if it's losing energy, what does that mean for how the electron moves? It's going to go slower and slower and slower, right? Otherwise, we're violating the law of conservation of energy, which still applies even down at the scale of atoms, right? So if it's radiating out EMR, that energy for that EMR has to be coming from somewhere, and it would come from the kinetic energy of the electron. Now, what did we say before about the moon orbiting the Earth? Or even just as you learned in physics 20, right? If you don't have enough tangential velocity, you can't maintain as high of an orbit. You come closer and closer to the thing you're orbiting. All of that acceleration, that constant acceleration, is going to keep emitting and emitting and emitting EMR. So what would the result be? Well, you would have your positive nucleus, you would have your electron, and since it's constantly accelerating, it would always be emitting EMR and therefore losing energy and therefore going slower and therefore not being able to maintain an orbit. It would crash into the nucleus. If Rutherford's model were correct, then the universe as we know it would not exist. All matter would pretty much instantly collapse. It is not stable. So thankfully, this is not the truth, and Rutherford actually even knew this, like I said, right? But this model did work to at least further our understanding a little bit. So this was kind of put in place with the knowledge that pretty soon we're going to replace this. So what does the resulting model look like? It's actually probably the most commonly used model of the atom. It's the one you see on cartoons and stuff probably the most, right? So note the electrons are in an orbit around a positively charged nucleus. Notice I haven't called them protons or neutrons. We know now that's what they are, right? But Rutherford hadn't concluded this yet. He actually would go on later, years after this, to sort of discover the proton, and he actually got to name it. But I want to be clear, the gold foil experiment did not lead to the discovery of protons and neutrons. It just led to this discovery of concentrated charge and mass at the center of an atom that we called the nucleus. Those are the big ideas that we can kind of get through intuition, but as promised, let's just kind of look at how Rutherford did end up calculating the size that this positive charge would have to have. So the main thing Rutherford is credited with, again, is the discovery of the nucleus for the gold foil experiment. Okay, so to get a feeling for how he just determined its size, well, these incoming alpha particles are moving and they have mass, so they will have kinetic energy. Now, clearly, because they were deflected or rebounded, the nucleus is providing a repulsive electrostatic force, right? Fe is kQq over r squared, Coulomb's law. So what is that force doing? I want you to imagine a rebounded particle. Okay, that's probably the easiest one. So one that comes straight in and then deflects back at an angle of 180. Okay, well, all it's doing is taking that alpha particle's kinetic energy. The force is doing work on it to take away that kinetic energy and then end up turning it into electric potential energy. Okay, so the work the force is doing is Fd cos theta, and that's the change in energy. So just a note here, this formula, it's derived using very basic calculus. You'd be able to do it if you took Math 31. So you don't need to use it, but I'm just showing you it so you can kind of better understand Rutherford's conclusions. And you can still kind of see the fingerprints of these equations up here, right? These are what goes into deriving this with calculus, and you can kind of see the remnants of it there, right? Make d r, which is really what it is anyway. It's just that usually we use a d instead of an r for this one. So if we set the energy equal to all of a rebounded alpha particle's initial kinetic energy, which has now become electric potential energy at the point where it's going to stop and turn around. Now think about what that d must mean, or what we can interpret it as. That has to be the maximum possible size of the nucleus. Not saying it is the size of the nucleus, but it's the biggest the nucleus could possibly be, right? Why? Well, the particle can't have actually moved into the nucleus. So we can work out the electric potential energy it gets by getting very, very close, right? By using this equation, by getting very, very, very close, the potential energy becomes big enough that it overcomes the kinetic energy and the particle stops, and then it goes back to kinetic energy as it's repelled away from the nucleus. And so with that logic, Rutherford kind of used this relationship, found the maximum possible radius of the nucleus, and he found it was about 10 to the minus 14 meters, which is at least 10,000 times smaller than the radius of the entire atom. Most atoms on average are about 10 to the minus 10 meters. 1 angstrom, we call that unit, okay? So think about this, 1/10,000th of the whole atom is actually occupied by the nucleus. Most of an atom is empty space. To kind of put that in perspective, if you could take an atom and blow it up to the size of a football stadium, okay, and like a professional football stadium, then the size of the nucleus within that football stadium would be about the size of a marble. Another one that always blows my mind, if you take all the empty space out of all the atoms in a human, and then do that for every human. So take the entire population of the Earth, all 7.5 billion of us, okay, and remove all the empty space from all of our atoms. Do you know how big the entire human population would be? It would be about the size of a sugar cube. Atoms are mostly empty space. Pretty weird to think about. The things that make up everything are actually mostly nothing. Okay, that wraps up topic 2. If you're looking for practice with that stuff, check the Google Classroom or the agenda for specific questions to work on that.